So welcome back to the Calculus Analytic Geometry. So we will carry on our discussions over the optimization techniques and learning some more applications of the derivatives actually. So what we did in our last class, we kind of discussed in detail, okay, in a very gentle and in a simple way. We tried to make sense of what do you mean by the absolute and local extrema. Okay, so this is what that we covered like that, and by extrema I mean maxima and minima for a given function. Okay, and then we understood it intuitively. We wrote definition based on intuitions. We did some examples, and then we discussed what do you call the critical points. Okay, and we discussed that every maxima and minima must be a critical point, but it is not necessarily that every critical point must be a maxima or minima, because a critical point can also be a point of inflection actually. So we discussed that. Then we discussed, we ended our discussion on what do you call so-called closed interval method. Okay. It's really a very simple method for finding the absolute maxima and minima of a given function, but today we will kind of cover the more sophisticated methods actually for finding the extrema. So this is a short snap of the things that we covered in our last class. So what we are going to do today, so the agenda for today is to consider some more optimization techniques. So in particular we will talk about a very interesting theorem, mean value theorem. Okay, we will not prove it, we will just do its intuition and do some things based on it. Then we will talk about increasing and decreasing functions. We already know a little bit about when a function increases and when a function decreases. Okay, but we will today know that, I mean, if you know that on what interval, on what part of the interval function is increasing and decreasing, then you can actually make a rough sketch of that function actually. Then the key thing that we're going to do in today's class is two techniques. We'll learn two new interesting and beautiful techniques for finding the maxima and minima. So these techniques are going to be first and second derivative tests. Okay, derivative tests. Okay, and then we will hopefully talk about the indeterminate forms. Okay, so if you have to compute some kind of complicated limits for which it is not obvious to compute limits, then you will see that derivatives basically also help us to compute the complicated kind of limits actually. So we will do indeterminate forms, okay, and in particular we will emphasize on what do you call it, L'Hopital rule actually, so it's called the L'Hopital rule. L'Hopital rule to find the limits in case of the indeterminate form. So pretty big agenda, but hopefully we will cover everything today in these set of discussions actually. So let's start with our first objective. Imagine you have two cities. Okay, so imagine this is city A and this is city B, and this is a highway going between the city A and city B actually. So you may assume it that this A is, so this highway is like a motorway actually between these two cities. Let's assume that the distance between two cities is 300 kilometer per second, 300 kilometers, okay, and let's assume that this road between the city A and B is a very busy road actually, because there is a lot of traffic and there is a lot of rush actually. The maximum allowed speed that is, you know, allowed on this this road is really, what do you call, the max speed that you can take, so a car, a truck or whatever can take on this road is max allowed speed is say 99 kilometers per hour actually, okay, 99 kilometers per hour. So you can't go, or you shouldn't go between above 99 kilometers per hour between two roads actually, okay. Imagine you entered into this road, okay, at say, I mean, if so one thing that I should say, that if you go beyond say 99 kilometers per hour speed, you will have a challan actually of, you know, say for example some 1,000 rupees actually. So imagine you entered into and you left the city A, in other words precisely entered into this road at say at 9 a.m. in the morning, and you reach at the city B 12 of the noon actually, okay. Obviously when you are, you know, traveling on the road, you sometimes slow down and sometimes you move fast, and sometimes you want to sometimes you want to move fast, and sometimes you want to slow, and sometimes you want to move normally. So you know, it is not you know, it is not always possible to have a smooth ride, okay, on a road with a heavy traffic actually. So imagine you covered this. Now the question is, what would be your average speed? Average speed actually. So it's not difficult to calculate. So I have covered say 300 kilometers per hour. Kilometers in 300 kilometers in 3 hours. So my average speed is going to be 300 by 3, which is equal to 100 kilometers per hour actually. Okay. As I said, on this road there is a rule that at any instant, if you go beyond 99 kilometers per hour, or you hit, for example, 100 kilometers per hour, you will have to pay the challan at, for example, B actually. Now you covered 300 kilometers in 3 hours, so your average speed is 100 kilometers per hour. Now keeping in view this average speed, can we make a guess actually that between A to B, while you are traveling on this road, there must be one instant actually. There must be one instant where you hit, for example, the speed of your speedometer shown, what do you call, the 100 kilometers per hour actually. Okay? So it's pretty much intuitive actually. So there must be. So in other words, if your speed is always below, say, 99 kilometer per hour. Okay, so imagine you are arguing with the traffic police officer that no, I haven't, I haven't went above 100 kilometers per hour. Then the police officer, the traffic police officer, can argue that your average speed is 100 kilometers per hour. That means that between A to B, there must be an instant where you must have hit what you call the 100 kilometer per hour speed actually. Because if your speed is always below 100 kilometers per hour, for example, then you can't cover the 300 kilometers in 3 hours. So if you have covered 300 kilometers in 3 hours, okay, that means that there must be at least one instant between these two cities in these 3 hours where you have went above what you call 100 or where you have went above, say, 100 or more than 100 kilometers per hour actually. Okay. The question is, okay, so this is pretty much what you call intuitive actually. So if your average speed is 100 kilometers per hour, there must be an instant where you must have hit this average speed actually. Okay, you can't cover 300 kilometers, okay, in 3 hours while your speed in below 99 kilometers per hour speed actually. So if your speed is below 99 kilometers per hour, there is no way that you can cover 300 kilometers in 3 hours. So if you have covered 300 kilometers in 3 hours, that means there must be an instant where you have crossed what you call reached or crossed the 100 kilometer per hour speed actually. Okay, so that means you have to pay the challan actually. Imagine now you want to develop an algorithm actually. Instead of doing this, okay, with, say, police officer manually, okay, what if you want to, for example, assess a technology, okay, you want to write an algorithm, you want to create a machine that as you enter from A, okay, at a certain time and you leave from B at a certain time, it calculates the average speed and makes a decision, automated decision actually. That machine makes an automated decision that whether you have violated this rule or not actually. So if you have violated this rule, okay, then the machine, okay, should give you a challan actually. Okay, it should give you the challan. The question is how to create a simple algorithm that can do this. And the answer is, here's a beautiful theorem from mathematics, from calculus, what do you call the mean value theorem, that if you implement that, if you make an algorithm based on that, you can easily create such a machine actually. Okay, so what is mean value theorem? So MVT. Let's start with MVT. It really, puts in this observation in the form of a mathematics actually. Okay, let's start with an intuition. Okay, let's start with an intuition. Imagine you have this x-axis and y-axis. Okay, and imagine you have a continuous function that is defined on a closed interval a to b. Okay, so I have a continuous function that is defined over a closed interval b, and that looks like this actually, something like that. Okay, something like that. Now, and so it's continuous, but there is also one assumption that that this curve does not have a kink actually at any point, so it's differentiable as well. So it's smooth actually. Okay, so it doesn't have a kink, it doesn't have a corner. Okay, so it's not like this actually, that where you have, you know, you have a corner. Okay, so if you have a curve, okay, that is continuous between the interval a to b, okay, and it does not have a kink or a corner, okay, then what would be the average, you know, value that this curve has achieved actually? So if for example, if this is representing the position of the particle, so x is say time axis, or s is representing what you call the position, okay, then what does this show? That okay, you started with a little acceleration and then you went, your velocity increased, and then your velocity started decreasing, and then it decreased more, and then again it started increasing actually. Okay, so that would be like, the question is, what would be the average velocity here actually? The answer is that yes, you can easily compute it. You just need to know that okay, where I was before, from where I started. So if this is A, you know, corresponding to this point, this is f of A, okay, and if this is B, corresponding to point, this is what do you call, say f of B. So imagine this function is f of x, okay, imagine this function is f of x. Then what is what do you call the average change? You know, what is the average change in velocity? For example, you have if your position is changing according to this curve actually. So how you can compute this average change? So you're going to say that okay, how far you have went and how high you have went actually. Okay. So in other words, how much distance you have covered in how much time. So for example, here I covered 300 kilometers in 3 hours. So if I want to compute the average, I need to divide the both quantities. So if you want to compute this average, you know, this average, what you need to do, the average value of the function in this interval is what? F of b minus f of a over divided by b minus a. This is the average value of the function in this interval actually. Okay. Now if you draw, for example, a secant line, okay, secant line that joins these 2 points. Okay, so let's call this, so this is a secant line that joins these 2 points actually, okay, which is kind of give you an average change actually. So this is giving you an average change change in the position, change in the s actually. Okay, so this is what is giving you the average change. Now, what does mean value theorem is telling you? In this interval, there must be a point where this average change is equal to the instantaneous change actually. The average change is equal, change in the function is equal to the instantaneous change. In other words, if you have covered 300 kilometers in 3 hours by going on some speed, okay, sometimes you moved at 40 kilometers, sometimes 50, sometimes 60, sometimes 80, sometimes 85, sometimes 90, but you covered with different speeds 300 kilometers in 3 hours. Then there must be an instant where your speedometer has hit the 100 kilometers per hour actually, okay, which is equal to the average, you know, what do you call velocity, okay. So the same is the case here. So if this is representing, this secant line is representing the average value of the function, okay, the average change in the value of the function, then there must be a point where this change or the slope of this line is equal to the instantaneous slope of the curve. So for example, I would say that if I take, for example, this point, okay, and draw a line here, draw a tangent line here, the slope of this tangent line is precisely equal to the average change actually. So in other words, there must be a point C, okay, so a point C between A and B where the average change or the slope of the average change is equal to the instantaneous change actually at C. Okay, I know that the tangent line on a curve gives me what? It gives me instantaneous change. Okay, while this is representing what? Average change. So the mean value theorem is telling you if you have a continuous function defined on a closed interval and that continuous function is smooth as well, okay, there are no corners in it within A to B, then the average change in that function should be equal to, there must be a point between say A to B where the instantaneous change is equal to the average change. In other words, this slope, the slope of this line is equal to the tangent slope of the tangent line actually. Okay, so this change is like 300 kilometers per hour, while as with this intuition you deduced that there must be an instant between 9 a.m. and 12 of the noon where your speedometer in the car must have shown the 100 kilometers per hour. Okay, so this is precisely what it says. So the average change, so if the average change must be equal to a point in the interval where the average change is equal to the instantaneous change actually. Okay, the average change is equal to the instantaneous change. So this is what it tells you, and no matter what curve you make, it doesn't matter. Okay, no matter what curve you make. Okay, so the thing is that it should be continuous actually. It should be continuous. So this is what you call average change. So I would say that is there a point on the curve where if I draw a tangent line, that tangent line is parallel to this secant line? The answer is yes actually. Think about it. So one point is this, okay, one point is this. On this point, if I draw a tangent line, okay, if I draw a tangent line that is parallel to what you call the secant line, and interestingly there is another point actually where if I draw a tangent line, that tangent line is also parallel to what you call parallel to the tangent line actually. Okay, are you getting the point? So with this intuition, so this is a mathematical way of understanding it. This is one of the interpretation of this mathematical description, and now I would like to write what do you call a precise statement of the mean value theorem actually, that what does mean value theorem is telling you. So pretty interesting lemma, pretty interesting theorem actually, and it says it has lots and lots and lots of applications actually. Okay, practical applications within mathematics, within sciences, lots of interesting applications. So what this theorem is telling you? MVT. Okay. So the statement says that if f is a function, okay, if is a function, okay, that is continuous, that is continuous on the interval A to B, and it doesn't have a kinks, and how can I say it mathematically, and differentiable, and it is differentiable on all points between A to B, okay, not including A to B, then there is a point C, there is a C between in the interval a to b such that at this point, if you compute the instantaneous change or the slope of the tangent line, then this instantaneous change at this point is equal to the average value of the function over the entire domain actually. So the average is achieved by the instantaneous change. Okay? The average and instantaneous change are equal. So function is continuous, and it's differentiable. There is no kink in it. Okay? You can differentiate at all inputs that function. Then there must be a point between the interval a to b where the average change is equal to the instantaneous change actually. Okay, so this is what the mean value theorem is telling you. So I kind of give you already an example here. Okay. Next. Now we'll talk about, increasing and decreasing functions. Imagine a function is increasing, so it goes like that actually, for example. Okay? It goes like, I would say that, imagine if I have any function, so that sometimes decrease and then increase, and then decrease, and then increase, and so on and so forth. The question is, for example, I can have a graph and know that, okay, where the function is decreasing, where increasing, and when decreasing, and where increasing. So, I can see the function and I can judge actually that where the function is increasing and decreasing. But imagine I have an abstract function, f of x actually, which I don't know in general. Then without looking at the graph, how can I say that where the function is increasing and where the function is decreasing actually? Okay? So here is something what you call interesting about decreasing and increasing what you call functions actually. Now say on this part, say function is decreasing, okay? So it's decreasing and then it stops and then it starts increasing actually. So in this part of the curve, say if you draw the tangent line actually, how does the tangent line would look like? Think about it. So let me make it a bit more explicit. Okay. So if you draw a tangent line at these points, what you can say? That draw a tangent line, so on and so forth. So the curve, the points, the place where the curve is decreasing, if you draw the tangent lines are going to have negative slopes actually. Okay? Negative slopes. And slopes are basically derivatives. And how about when the function is increasing? So here, like this is like a critical point where function has stopped moving. Okay, so this is critical point. And how about all these points? What is happening to the function at this point? Okay, so think about it. When the function is increasing, what is happening to the, what do you call, the slopes of the tangent line? You will see that the slopes of the tangent line are always positive. Okay, so, and the slopes are derivatives. So this gives a kind of a hint actually that if you have a function whose graph you don't know and you want to know that at what point the function is increasing and at what point the function is decreasing, you have to look for what do you call three things are really, three things mainly. First, look at the point which are the critical points. Say for example, this is a critical point, this is a critical point, for example, and so on and so forth. So you